Okay, let's discuss about this question. LeetCode 449, serialize and deserialize BST. So what's the meaning of this question? So given this binary search tree, so what's the meaning of binary search tree? So it means that the elements on the left side of the root is smaller than the root. All the elements on the right side of the root is all larger than the root. And also the rules apply for all the elements in the tree. Okay, so the question is asking you to serialize. What's the meaning of that? So you have to turn the tree into a continuous stream. It's kind of like to make it more compact. Yeah, right. And then okay, you can use the pre-order, in order, post order, and also you even can use other ways like from top down and from left to right. Okay, you can do that. And after that, and now you have the input, you have the serialized input, and then you have to turn the serialized input into the this tree. It means that you have to deserialize this input and reconstruct the output. So as long the output is exactly the same as in the previous input for the serialization. Okay, so that's the meaning of the question. So how can we do that? So here is a strategy I want to share with you guys. So given this binary search tree, so I will use the post order to serialize the binary search tree. What's the meaning of that? So the post order is like a left, right, middle, right? So it means that I'm going to serialize this part, and then the right part, and then the center. So that's the result. So it means that the orange color means the left side of the root. All right. Okay, let's change the color here. And the blue color is the right elements in the binary search tree, which is red. So now the next step is that we have no problem to serialize because we can always use the post order. It's like so it's straightforward. So the next step is we want to deserialize, right? So how can we do that? So firstly, we need to initiate a stack. So we put all the elements in the stack one by one. Yeah, one by one. So now so this is stack, and also we want to set an upper value and a lower value. So the upper value initially is the maximum value of the integer, and the lower value is minimum value of the integer. And I will explain later why I need two variable. So initially, the pointer. So initially the pointer is point to the 50. So I will make 50 as the root of the final result, and after that I will move. Okay, firstly, because I picked this value, so I need to pop it out, right? So I move the pointer to this position, and also I need to because this is the right side of the tree. So all the elements in this part is smaller than the 50, right? So so I'm going to use it in this way to reconstruct the right part of the tree. So now the 60 is between this range, so I will put 60 here, right? Okay, so now 60 is ready, and now I will continue going this way, because now here is 60, so the lower bound is 60. So the 67 is in this range as well, so I will put the 60 here. All right, and now, okay, that's the point. Please pay attention here. So here is 50, right? So 55 is actually is out of bound. It's not here. So it means that the 55 is not belong to the further right hand of the tree. So the 50 is actually belong to the left side of the 60. So that's the reason we need to put 55 here. Okay, and so okay, now the lower bound is 50 pips. So now let's go to continue. Okay, that's one thing I just updated. So this one should be 1 because this one should be smaller than 3. So I updated the input. Okay, so all the input I should be updated here. Okay. Okay, so now the 40. So now the 40 is actually out of bound. So when it's out of bound, it means that the right subtree was actually reconstructed. So we will use the same logic to build the right part. For example, here. So here, so the 40 should be put here. And after that, we will go to 3. So the 3 is actually okay, 1 second. So in this way, actually, the upper bound was changed because now I'm going to build a build a left tree. So the left tree, the bound was actually updated, right? So it's actually since we have 40, so the bound is like this. The upper is 40. So when we have the 3, so the 3 is actually in this boundary. So the 3 should be here. Should be here. Should be here. And then we find the upper bound. So now we found the upper bound is 3. Okay. We find this is 3, and then we found the 9. So the 9 is actually is larger than 3. So it means that the 9 is no longer belong to the right subtree of 3, and then it belongs to the right side. And after that, the lower bound is actually 9, right? And then we find 1. So the 1 is actually out of bound again. So I will put a 1 here. So basically, this is the strategy how we reconstruct, discuss about the code. So basically, we need the post order to turn the binary search tree into the in the series, right? So this is so when we do the serialization, we need this function. Okay, so when we do the serialization, you given the tree root, and then we put the root into the post order, and then return the string builder, right? So the string builder will then turn to string. Okay, so in this way, so this is the serialization step. That's very simple. The difficult one is that we want to do the deserialization. Okay, so when we do the serialization, let's say the input can be something like this, right? Something like this. So when you have the input like this, and then you may want to put this into the stack. So when the data is empty, actually, then we need to return no, right? Because what's is empty? The empty is that when we check the string is empty, is that the learns is actually equal to 0. And then we initiate the stack, and then we put all the stuff into the stack, right? So now I'm going to use a pointer at the top of the element, and then each time I'm going to pop one element out. Yeah. Okay. Let me see. Okay. So this is the one. In this way, we put all the elements in the stack, and after that, we use a helper, have the lower bound and upper bound and the stack. Then how can we do this? So let's dive into the function. So if the stack is empty, so it means that there's nothing to cope with, right? Otherwise, we will get the last elements. So here, okay, so when we want to get the last element here, so the pointer point to the 50. So we want to get 50 out, and then if the 50 is lower than the lower bound, so why we need this part? We don't actually need to compare with the upper bound. We only need to compare with the lower bound. All right. So because when you move your pointer here, for example, if you move your finger here, and then you find out that this pointer is smaller than the lower bound, which is what? Which is 50. Okay. So this smaller than lower bound. So it means that now we have completed the righteous construction. So now we will begin the left tree construction. Okay. So and after that, yeah. Okay. Let's start from this place. So when we get one element out, so we will move the pointer here, and also we need make this 50 as a root, right? So we make the 50 as a root, and after that, we're going to build the right subtree for the 50. So how can we build a right subtree for the root? We're using the helper. So it is a DFS. So we go to deeper, but the problem is how we use the parameters. So we always use the same stack. So the stack itself will keep the same all the times. But when we do the write, the lower bound should be the value itself, because all the elements on the right should be larger than the 50. So the 50 is now is a lower bound, and for the and for the upper bound is always the largest stuff. So after we finish all the stuff, you see we need value. We need to check if the value is smaller than the lower bound. We need to check if the value is smaller than this. If once we find it is smaller than 50, for example, when we come to this position, 40, is smaller than 50. So it means that we know that this part is complete, right? So now I can start to construct the left tree, right? So the left tree is upper bound is 50. Yeah, so we're going to using this way to reconstruct the tree. This code, so we need to serialize again and then deserialize. And for each function, we need a helper function for that. For the first help function, it should be the public void helper1. All right. So the helper1 is actually trying to help you to do the post order traverse and then to make them in the one stream, right? So in this way, I'm going to firstly we need to check if I think we don't need to check that. We just need to put them in the helper1 and the SB, and this SB is the stream builder. Stream builder SB equals to new stream builder. Okay, and also we need to put it here, stream builder. And after that, we need to return what? Return the SB to string. Okay, there's a corner case we don't need to cope with. Is that what if the root is actually equals to none? Yeah, in this way, if the root is equals to none, so when we run the helper1, so it will run nothing, because here we will do a changing checking is if the root is to none. If yes, I'm going to return nothing here. Otherwise, we will to further to do the helper1, helper2, right? Still helper1. Okay, so for the helper1, because I'm going to do the we are doing post order, so it means that we will left, right, middle, right? So in this way, let's see, we will get the left first and then get the right first, and then to get what? Get center. So the center is the root value plus. Okay, I will further later explain why we need the comment here, because we need a comment to do the deserialization, right? Otherwise, we cannot differentiate all the elements here. Okay, so that's pretty much for the serialization. So let's continue to do the so let us do the deserialization. So the first step is that we're going to check if the data is empty, right? If it is empty, then I'm going to return no, right? And otherwise, we will we're going to stack have a dequeue string. So we actually need a stack to to do linked list. Right, so we need this, and for all the current, right, it's what, it's data split this. So after we split this, so we have the stack add what is, we are going to add integer parse int, right? We're going to move to the stack, and after that we're going to return is a helper2. So the helper2 will do what? The helper2 will do there's the lower bound, it should be the integer main value. So this is the lower bound, and after that we pass the stack to the helper2. Okay, so how the helper2 will do the work? Let's say we have the tree node helper2, and so we're going to have int lower bound, and also the deq should be deq what, stack. All right, and after that, if we found the root, if the stack is empty, right, and so we're going to return none. Otherwise, we will get the let me see, the deq should be integer. Okay, so we're going to integer current is equal to stack get last element, right? So if the current is smaller than lower bound, okay, we will discuss this later. So if it is smaller than the lower bound, so it means that we have already completed the right subtree, right? But after that, we will stack remove last, right? So if and so the root and then also we're going to make a root should be the current value, right? And then the root's left equals to, right, the right is equal to helper2. The lower bound becomes to current, and then also we use the same stack. All right, after that we use the root left and helper2 also current stack. Please pay attention that because now we have round for the construct the right tree first, and after we construct the left tree. So that's the reason, even though the stuff here is the same, but the answer is actually makes sense. Okay. So, but when we run this part, how can we understand that actually for the left tree, the lower bound should be the previous lower bound. So the lower bound should be passed here. Yeah. So here's the way we build the left tree, because the left tree is actually should be always lower than the current root. But for the right tree, if the current value is smaller than the lower bound already, and in this way, we're going to return none, because if the so this is the lower bound, right? This current is this function lower bound. But if we found somebody in the stack is actually smaller than this one, so it means that we're going to return nothing here. There's nothing to return. So the element should belong to here. If the current is smaller than the left bound, it will directly return none. So it will not remove the last element. So the last element will pass to this part. Okay, let's run if we can pass the example. Let's 21. We should update the type here, and it is 50. So maybe it should be updated integer. No, it's not a problem. Should I add DQ? All right. So I have to return root, right? Okay, I passed.